Okay, so any question? I think this time was, oh, it's really loud. Hello. Yeah. This time was midterm, and I think midterm is graded, so yeah, I will look at the result sooner or later, and we will have well a small review of how everyone did on midterm, and I guess if you have question on midterm, you can also ask now. If not, then excuse me. If not, then this time we go over quantum universality. Where is everything? Yeah. This time we go over quantum universality, and we prove that. Okay, so let's go over this file again. Quantum universality, and so we have this really long proof, and the end result was that we say Hadamard gate, T gate, and C naught is universal for quantum computation. Yeah. And this is because Hadamard T can approximate any single qubit unitary, and together with C naught, and we say any single qubit. So if you can do all single qubit unitary plus C naught, then it's universal. And that's many step construction, and it's quite brute force. We kind of do this Gaussian elimination for unitary, and we break it into a whole bunch of different matrices. Okay, and yeah. Anyway, that's the end result. And if there is no question about quantum universality, now let's go back to algorithm. Okay, and so back to this quantum circuit file, we have. Talk a lot about quantum circuit. So quantum circuit, we have those wires and the gate. So wires, each wire is a qubit. They will not disappear basically. And there are gates that are unitaries. So unitary matrices acting on the wires. And you have this thing. You have done some, and we go over multiple examples of what happens to a quantum state when you go through a quantum circuit, and there are also midterm questions on it, so everyone should be very good at calculating quantum circuits now. And anyway, so now we know quantum circuits, then finally we can talk about quantum algorithms. It seems so, although so there are some short review about quantum universality here once again, but I think we can skip it. So yeah, as we say, so C naught plus arbitrary 1 qubit is universal, and C naught Hadamard T is universal, etc. And anyway, go back to quantum algorithm and quantum circuit. There is actually some extra elements we want to talk about in quantum circuit. That is this idea of quantum oracle. It's actually a generalization of classical oracle. And so it's a bit funny, when we talk about classical circuit, we kind of think like, so let's go to circuit. So right, so circuit, and we kind of think the circuit solves some problem means that you have some input, you will get some output. So input put at the start of the circuit, and and some bit will be output. Okay, and you kind of expect quadrant work like this, but there is a funny way to give input that is, you will give input as one of the gates here. Okay, yeah, this is a really funny thing to do if we put it this way, but it makes sense because we kind of think the computation, so hard part of computation is concentrated on some subproblem, and you just want to ask how many of those subproblems you need to solve to calculate your thing. And so that really hard subproblem, we kind of abstract it into this oracle. Okay. So yeah, so we have this funny oracle box that calculates some function for us, and we want to ask ourselves, how many of those oracles do you use? Can you calculate your problem? Okay. So yeah, so as we say, this is a generalization of classical oracle. So this oracle will compute some function for you, And so if it's a classical oracle, then you input some x, and then you output some f of x. Okay. Okay. And yeah, so this is really confusing because okay, so there are two things. So you think this oracle as computing some f, but you also think this whole f as a string. Okay. So there are kind of two input here. Okay. I guess that's a fixed input as the input to this f here. Okay. So you think this oracle computes some kind of function f for you. Okay. And so there is an input of this f, that's x here, and so quantum oracle is this unitary that you take input x and okay, so the input x stay x because it cannot disappear. Classic oracle you can kind of just erase x here, but quantum oracle is reversible, so x stay here, and you compute f of x to another register here. Okay, and it's reversible, so actually you cannot just have f of x here. So you want the other register is where you write the output. It might start with something y, although you kind of feel you want it to be 0 at start, but actually sometimes not having 0 here is even better. Okay, but that's for later. But anyway, so here is the register where you write the answer, and so you have this y o plus f of x here, and so this is reversible. And okay, so this o plus is a bit ambiguous here, but for one bit you can think of this as XOR. Okay. Okay. So for now we think f of x as maybe one bit output. Okay. So then this is XOR, so 1 plus 1 equal to 0, and 0 plus 1 equal to 1, and 0 plus 0 equal to 0. And when there are more bits here, then it depends on how you want to define it. Okay. So anyway, this thing you can compute f of x, and it's reversible. Okay. So yeah, so this is a reversal gate because you have an xy pair, and yeah, or you have this xy or plus f of x pair, then you can calculate f of x here and add f of x again and get back to 1. Okay. And so basically the requirement here is yeah, you want this y plus f of x to be 1 to 1. So kind of you want y, maybe change the color. Yeah. So reversible means you want y plus f of x, and you plus f of x again equal to 1. Okay, you want this kind of addition. Anyway, yeah. So this is an oracle. You will compute this f of x, and maybe stay here. Yeah, you will compute this f of x into this register. So if you input x here and a 0 here, then you will get x output and the f of x as well output. And if we write it in this algebraic way, then it's like this. So you have x on this xy input state, both computational, then you get f and y plus f of x. Just writing this picture into equation. Okay. And okay, but no interesting thing is this thing is a quantum gate, so you can do superposition. And so weird thing can happen. Say you have 0. So here x y we kind of think as a computational basis. But now if you put actual quantum state as input, then you can get a weird entangled output. So for example, I put a plus here and a 0 here. And we know plus is 0 plus 1, right? Okay. And oh, so I read this wrong. Sorry. Okay, so this is confusing here. Okay. So it's a 0 plus 1 on the first qubit and a 0 on the second qubit. So at the start here, you will get 0, 0 plus 1, 0. Okay. So you expand everything computational basis, as we say, is 0, 0 plus 1, 0. Okay. And then you go through this UF, and so what's the output state is you do UF on the computational basis 1, 1. So UF on 0, 0, well, then 0, as we say, is state 0, so x go to x. And the second 0 will be the y, so this is 0 plus f of 0, right? F of x equals 0, so this is f of 0. And okay, and we assume this O plus 0 equal to the same thing. Okay, so this is at 1 bit. Yeah, and what about the second register? Then you have 1, so 1 x equal to 1, or 1 stay 1, and sorry, the second component. And so first register 1 stay as 1, and the second second register you got 0 plus f of 1. Okay. So this is 0 plus f of 1, and that's just f of 1. Okay. And yeah, so you see this has this weird superposition effect that classical Oracle don't do. Okay. So you have a superposition of input, you will get a superposition of output. It's not clear how this is useful, so right now, but we'll see how it's useful for when we actually design algorithm for different things. Okay, and as we said, the simplest example is using f of x as a Boolean function. So this f0, f1, or f of x is 1 bit. The Boolean function is you have n bit input and you get 1 bit output. Okay. And this O plus now is very well defined, it's x over here. Okay. And and so this Oracle thing has many names. Okay. And I will interchange it through all the course. So it's either called Oracle or Oracle because it's like something that give you answer. So you pay something to give an answer. Okay, and so we think that each placing each of these UF getting into the your circuit costs one unit of something. Okay, and so you pay 1 unit to call pay 1 coin to call the Oracle, and you get 1 answer of f of x out. At least that's classical, right? So when classical, you use these all f1s and you can compute f of x and 1 of x. And when it's a quantum Oracle, then it's a bit tricky. You kind of also get 1 copy of x out, but as we see here, you can get a superposition of f of 0 and f of 1. And this is where you can get a quantum speed up. And so some bad teaching of quantum mechanics will say, no, you can get the equal superposition of all f of x here as an input, and you will get a superposition of all f of x as an output. So you can compute everything parallelly. But that's actually not true because you do measurement on this thing, and you only get each one of the outcome as a very small probability. So yeah, so you need to work harder to actually get quantum CPR through those UF or OF, as we will see. Okay. So anyway, that's Oracle, and it's also good query. Okay. And okay, so query is actually a verb. So the way to use this word is should be query on Oracle, but but also sometimes we use it as noun because you can, yeah. So it's either a verb, is both a verb or a noun. Okay. And also we will call this as a black box because we kind of think this UF as a black box because we don't care about how the quantum circuit realizes this function f. Okay. We just say there's a box here and it calls something to construct it, and if it's here, then it will give you some answer. Okay, so black box. So you don't look at the inside. Inside is black, and it's just a black box here, and you can give it input, and it will probably give you output. Okay. So yeah, so this is the Oracle thing that we'll see quite a bit about, and I think so this is kind of out of Nielsen and Tron because Nielsen and Tron don't like Oracle that much. But yeah, but this is kind of my research area, and a lot of computational theory is around these oracles. Okay, so Oracle query black box. Questions so far? Okay, and okay, so now we have a really confusing thing. Okay, so this u of f, we can think this whole function as an input. Okay, because we can list out the truth table of your f as a bit string. Okay, so yeah, So this is really confusing. There are two different inputs in here. Okay, so the input, so there's a whole function f as an input, and there is also this x as an input. Okay. Okay, you also have this x is the input to your f of x, right? And yeah, so this is really confusing, but those two inputs are different. Okay. Okay. So what we'll do is we'll think the truth table of f as a bit string input. So let's say we count from 0 to we count from 1. Okay. So possible x is from x is a small n bit string, right? So there are 1 to 2 to the n possible x. So let's count x from 1 to 2 to the n. So f can have okay, yeah. So x can be like this 1 to 2 to the n, and for each x there is a possible f, right? Because f is well, the definition of function, right? So definition of function. So I'll just write it once again. Remember f is from 0, 1 to the n to 0, 1. Let's assume that we have Boolean f. Okay, and so this thing is x. Okay, so x is 1 to 2 to the n, or 0, 1 to the n. And so we say for each x, f can output you either 0, 1. So it's 0, 1 here, 0, 1 here, 0, 1 here, 0, 1 here. Okay. And so this whole f is determined by the truth table, right? So if you just list out every possible output combination, then you list every possible f. Okay. And yeah, so that's how we think a function as an input string. Okay. So if this function has this, so now this is 2 to the n bit string. Okay. Yeah. So we'll think this 2 to the n bit output string as the 2 to the n bit truth table as an input to our algorithm. So we'll put oracles inside our circuit and do computation on its truth table. And yeah, so that's a bit weird, but that's how we do inquiry algorithms. We have this f that's a small bit, that's a function on small n bit, and then we just think it's truth table as 2 to n bit. So usually we have this bigger n equal to 2 to n. So we think this whole function is this whole function is a really long input string, and when we do query, we kind of look at the location of different bugs. So a classical query, when you calculate f of 1, then you kind of open this box and know whether the output is 0 or 1. And let's say you query 3, x equals 3, then you know this box is 0 or 1, etc. Okay. And unfortunately, I think it's better to see this example. So we have example where n equal to 1, and small n equal to 1, and big n equal to 2. And we have a Deutch algorithm. Okay. And okay, so it's and in this example, we'll see quantum oracle is more useful than classic oracle. But that's first thing, what's the oracle? So as we say, we have f being 1 bit. Okay, so small n equal to 1, so f calculate 1 bit to 1 bit, and so small n equal to 1, so big n equal to 2 to the 1 equal to 2. Okay, so what are possible truth tables? So that's just list here. Okay, well, big n equal to 2, so possible truth table is 2 to the big n, so it's 2 to the 2. Okay. Possible truth table, let's say possible f, right? So we can just list a truth table here, possible f. So this is a truth table, so you just need to think about what's f of 0 and what's f of 1. And so possible truth table is both there are 0, 0, and this is 0, 1, and it's 1, 0, and it's 1, 1. Okay? So there are 4 possibilities. 2 to the n equal to 2. Okay. Okay. And so yeah. So if we have this 1-bit function f, then if has 1-bit input to 1-bit output, then there are 4 possible function f. Okay. And then we want to calculate something about this function f, and what we want to calculate is f of 0 plus f of 1. Okay. And so let's maybe this is here also. Okay, f of 0, or it's really small here. F of 0 plus f of 1. And okay, so if we have a 4 table, we can do a calculation easy. So 0 plus 0 equal to 0, 0 plus 1 equal to 1, 1 plus 0 equal to 1. And then 1 plus 1 equal to 2, but we have O plus here, means we are digit 2, so it's actually 0 here. Okay. And yeah, so this is the thing we want to do. Okay. And then our question is, okay, so the question is you only access your f through our box, right? Through our black box. So you can only know f of 0 and f of 1 from these funny boxes. So either you have this kind of query or this kind of query. So classical query, you can only look at f of 0 or f of 1. Okay. And it's pretty obvious that you need to query to know you need to query to know your f of 0 plus f of 1. So basically you need to learn the whole f. You need to learn f of 0 and f of 1 to learn what's the addition. Okay? Because when you query f of 0, maybe you get 0, then you know your f is one of these 2 possibilities. And but then you see that f1, if f1, so your function is these 2 possibilities, and but you see your output still have these 2 possibilities of 0, 1 because it depends on f1, and yeah, so you really need to query both f0 and f1 to know your f0 plus f1. Okay, but okay, so that's classical. But so now we see our first quantum speed up. So quantum will only need 1 query to learn f0 plus f1. So there is a funny quantum algorithm that will tell you it's either in this state or this state, and actually nothing else. You will learn neither f0 or f1. You just know f0 plus f1. Okay, kind of you look at the different dimension of your input. It's very interesting. Okay, and so we show people. Maybe let's see this. Then we'll get more idea about what we're trying to do. Okay, and so what we mean by quantum algorithm with 1 query is this. Okay, so we have some input state, as we say. So now input state is not actually input. Input is UF, and so the starting state of the algorithm just say that's 0. Okay, that's a standard thing we do in query algorithm because it can really be anything here. So let's say that's 0. Okay, and then we apply a whole bunch of get that has nothing to do with UF. So we have a header mark here, X get here, header mark here, and a header mark here. And when we say 1 query, means that in our quantum circuit, there is only one of these black box. So we only place 1 black box inside this whole circuit. Okay. And yeah, so we place 1 of the black box here. And the output will tell us f0 plus f1 here. O plus f1 here. Okay. Any question so far? Do people understand what we are trying to do? Okay. Yeah. And yeah. So well, this is the algorithm here. And if you're lazy, then I can stop here and ask you to verify it in homework. But let's actually see the verification here. Okay. And well. So verification, the starting step is what we have been doing. So we have some input state and we have some gate, and we calculate what's the state here up to this point. Okay, and so you see, really the first qubit and the second qubit are not entangled; they are just doing their own thing. So we can do the calculation separately. So we have hegemon on 0, and then the second qubit is okay. So remember time from left to right. So we have x on 0, then hegemon on this x over 0. Okay. And so hegemon on 0 is plus, hopefully everyone remember. And then we have x on 0 become 1, then hegemon on 1 is minus state. So we are basically having the plus state. So the 0 plus 1 for the first register of UF, and we have the minus state. So this is 0 minus 1 on the second register of UF. Okay. And the interesting thing here is this minus we are seeing very soon. This minus will do something very interesting when you pass it through F on the second register. Okay. And yeah, so this is really a quantum thing we do. So before, remember that we say we want to simulate something classical, and we just put the second register at 0, then we'll write f of x here. Okay. And but now we use a factor as a quantum gate, and we do something really funny. We put the minus state on the record register, and you will do something quantum as we see here. It's called a phase kickback. Okay. And okay, so we have the minus state here. Okay. And so we want to break it into this way just because we know this is easier to analyze. So we break plus state equal to 0 plus 1. This we already know. And we keep the second register as the minus state. Okay. So we have 0 tensor minus and 1 tensor minus. Okay. And now we analyze what happens when you apply our UF, so our oracle, on the computational base state tensor minus state. Okay. And yeah. Okay, so what happened? And so remember our formula is u of xy, uf of xy equal to x and y all plus f of x. Okay. And yeah, so well from here you see the x will stay the same, so x stay here. And okay, and now we break f this minus state equal into 0 minus 1. Okay, is 1 over square root of 0 minus 1. Okay, okay, and okay, so there is a 0 component and a 1 component, and both of them will get this O plus f of x, right? Okay, so 0 plus f of x, and then by linearity minus this 1 and O plus from f of x. Okay, okay, so this is calculation with a beam algebra. And yeah, so basically we are breaking into x tensor 0 and x tensor 1, then we do both of those, and then we by linearity combine it back. Okay, so 0 component get add f of x, and 1 component get add f of x. Okay, and okay, so now interesting thing happens. So what's this thing? We can kind of analyze this. There is some symmetry here. Okay, so well, there are only two possible f of x because we are Boolean function, so f of x either equal to 0 than 1. Okay, so if f of x equal to 0, then obviously you O plus 0, nothing happened, and this is still a minus state. Okay, but what if f of x equal to 1? Okay, and if f of x equal to 1, you basically negate here, right? So if x is 1, then this become 1. 0 plus 1 become 1, then 1 plus 1 becomes 0. So instead of 0 minus 1, you have 1 minus 0. Okay. And that just still the minus state with the extra negative sign. Okay, so yeah, so this is the interesting thing here. So no matter whether f of x equal to 0 to 1, the minus state still stays the minus state. Okay. Maybe I should do this thing. Okay. So the minus state still stays the minus state, except when f of x 1, you get the extra minus sign. And we can write this whole thing completely. So you have x tensor minus that always happen, and whether or not you get a minus sign, we can write it as -1 to the f of x. So this thing when f of x equals 0 is -1 to the 0, that's 1. And when f of x equals 1, obviously it's -1. Okay. And yeah, so this is called phase kickback, and it's a basis of a lot of algorithms in quantum computing. This whole line. So we'll see later that up to the Schwarz algorithm, Schwarz factoring algorithm actually has a root to this phase kickback technique. Okay. So this is a very important technique in designing quantum algorithm. Okay. And yeah. So once again, this is phase kickback. So you have your UF, and we find out that you put a minus state on your record register. Then your record register will stay a minus state, but your whole state will get a -1 to the f of x. Okay, phase. Okay, and so that's phase kickback. That's cool. And but let's go back to our Deutch algorithm. So what is our algorithm actually is? So we have this plus state as input to this UF. Okay, so it's 0 tensor minus and 1 tensor minus. Okay, and so that's a continuous algebra. Okay, so UF on 0 tensor minus and 1 tensor minus. And as we said, you will get a phase kickback. So the tensor minus stay the same, but you will get the -1 to the f of x. So x either equal to 0 or 1 here. So you have -1 to the f of 0 or -1 to the f of 1 here. Okay, and 0 tensor minus and 1 tensor minus. Okay. And then we are kind of done. Okay. So we want to combine. Okay, so they get both of those. Okay, so they both got -1 to a something phase, and we kind of want to combine those two terms. So we take our global term. So we take our -1 to the f of 0 factor out. Okay, so -1 to the f of 0 out, and then tensor minus you can linear combine them. So you just write tensor minus together. Okay. So you take out -1 to the f of 0, then you need to take out -1 to the f of 0 here. So you have f of 1, -1 to the f of 1 minus f of 0. Okay. And okay, so here the minus we are thinking in real number minus. Okay. Okay. And but now you think about what this state. So f of 1 and f of 0 are either 0 to 1. So really this minus and O plus is the same because it's because this thing to because -1 to some integer power, you only care about the even or odd of this. So you can really -2 here. And but anyway, the easier way to see this is you check all possible f0 and f1, and you see that this thing is equal to, so when f0 equal to f of 1, then obviously the subtraction is 0, then you get 1, right? So that's thing you get, this is you get 1 on this thing when f0 equal to f1. And when f0 not equal to f1, so this part is plus minus 1, and you get -1 to the either +1 or -1, you get a -1. Okay. So when f0 equal to f1, you get a plus state, 0 plus 1, 0 plus 1, that's a plus state. And when f0 not equal to f1, then you get 0 minus 1, that's a minus state. Okay. So the whole state is global phase that doesn't really matter, and plus tensor minus if f0 equal to f1, and minus tensor minus if f0 not equal to -1. Okay, that's the state here after you apply UF, and then we see that we are really close, right? Because we have two states. Because we have a two state here that are orthogonal, and which one happen depend on exactly what the thing we want to calculate. So if f0 equal to f1, then we get one case, and if f0 not equal to f1, we get another case. These are two cases that we want to distinguish. And those two states are orthogonal, so it's easy to distinguish them. You just rotate them into conventional basis state. Okay? And the thing to rotate plus and minus equal to 0 and 1 is Hedema. Okay, so it's very easy. You apply Hedema again, then you become 0 and 1 here. And yeah, so when you measure and at the end you will measure this register, and you see that you measure outcome 0. That means f0 equal to f1, and you measure outcome 1. That's when f1 not equal to f0. And yeah, so that's the proof of Deutch-Jones algorithm. You see that with one content query, you can compute this f0 plus f1, even though in classical computation, it's pretty obvious that you need two queries. So this shows you that quantum query is more powerful than classical query, because something that's only possible with two classical query you can do in quantum query, because you can do this funny superposition that tells you f0 plus f1 directly. Okay? Any question? Yeah. So this is the idea of quantum query. I guess this is an example of quantum query, and introduce a very important idea of phase kickback. And let's say a little more about quantum query, okay? Or quantum query complexity. So quantum query complexity study the thing that we see as above. So we think this f of x truth table as an input string. So just like here. Here we think this f is 1 bit, so we actually have a 2-bit input string. And we want to compute something on this 2-bit input string. And then we ask how many of those UF blocks we need to place in our circuit to actually compute it. Okay? So that's quantum query complexity. And as we said, it's a bit funny, we have two different inputs here. So we have f of x has a small x input that's a small n bit string, but this whole function f, so the truth table of this whole function, we think it as a string of big N equal to 2n bit input string. Yeah. So the truth table of f, and we think query are like look at of this f of x at different location. It is for classical query. But as we have seen, quantum query can kind of look at those positions in weird quantum superposition. And so the question in quantum query complexity is how much does the weird quantum superposition help you to determine your question on this input string. Okay. And yeah, so quantum query complexity asks you that how many of those UF you need to place in your circuit to compute something about f. So for example, in this question, we want to compute f0 plus f1. And maybe, so one of the functions you want to compute, people want to compute is like a generalization of that as a parity. So you have like, okay, so but we're actually counting from 1 to 2n, so it's a bit funny. So, but you can think about what's f1 plus f2 plus plus f2 to the n. So if you want to compute this, and then you can think about how many quantum query you need to place here. Okay. Yeah, so you have a whole bunch of different functions you can compute on this truth table. And quantum query complexity asks that. So you have a circuit, how many of those UF you need to place in your circuit to compute it. And usually we think it in this way. Okay. So we think, so obviously there are those UFs that you need to place in your circuit. And so when we're talking about query complexity, you will only care about how many UF you place. So between those UF, you can place arbitrary U. Okay? So those U in between are arbitrary. So they can be like even require many elementary gates to construct. We don't care. We only care about how many UF you place in your circuit. And because all those U are arbitrary, you can just say the input the starting state as O0. Because whatever starting state you want, you can make it from this U0. Okay? And yeah. So you start with O0, then you have those layers with arbitrary U that doesn't depend on f, then uf, arbitrary u, then uf, etc. And at the end, you do measurement, and hopefully you get your outcome. So it's like some big f of f. You want some function of this f, okay, like this. Okay. And yeah. And so motivation. So why we want to do this? I need to do this again. So what we want to do this is a very basic idea. Is approximation to time complexity. Okay. Okay. So remember when we talk about computational complexity, we say there are space complexity, there are time complexity, and usually we want to study time complexity. But unfortunately, time complexity is very hard. So we settle to compute this query complexity. Yeah. So the time complexity here. Yeah. So time complexity is hard. So we find out that for some question we can analyze it as in terms of this query complexity model, and it's actually a pretty good approximation. So we focus on how many of the hard part of so we think the quadrant has some hard subpart, and we just think as other, so how many of those hard subpart do we need to do for your algorithm to solve your actual problem? Yeah. And then because of the black box structure of the query complexity is much more analyzable than time complexity, because you can do some information theoretical thing about it. Okay. Yeah, so it's a kind of hard part of algorithm. And so this thing's a bit funny, but actually it's a pretty good estimate, I would say. Although obviously there are examples where time query complexity and time complexity differs a lot. But usually they don't differ too much. Okay. And as we said, excuse me. As we said, a very special feature about quantum query algorithm is you can do phase kickback. That is, yeah. So you can always write a phase version of your algorithm. Yeah. So I think this is probably your homework. And so you can show that by using phase kickback, you can get this phase version of your quantum oracle. So instead of the so remember we have a UF xy equal to x, y, or plus f of x. You can have your f of x on your phase. So you can have UF on x equal to -1 to the f of x. But actually this is a bit weaker than this thing. So what you want is you want UF of some control and x, and so you get -1 to your f of x only when control equal to 1, and when control equals 0, then you do nothing. Okay, so you can have this control phase state, and you can show in your homework that is a UF tilde and the UF, so the phase version and the standard version of Oracle, and there are one-to-one transition, and basically you get here to, so basically you get from UF to UF tilde by doing phase kickback, and you can think about how you reverse phase kickback to get back to this thing. Okay, is the homework. And any questions so far? Hopefully everyone get the idea of quantum query. And anyway, we have 5 minutes, so let's talk a little more about this classical versus quantum query. And so I said those queries, either classical or quantum, they are black box to compute some. You think about compute some small function f of x for you. And so classical is just you have some input x, and you go through this query box, and they will tell you f of x, okay? And you put in classical circuit. And quantum query, then it's funny because it needs to be reversible. Okay, so you cannot really erase this x. Okay, so yeah, it's funny. because let's do a little digression. Because the content is reversible, right? So even if this f of x is reversible, then it's not quite possible to do this x2. We still think it's not reasonable for quantum to have x and uf to f of x, because we think that there might be one-way function. Right? So there are some functions that's reversible, but that's one-to-one, but we think it's very hard to reverse. And so it's not reasonable to assume you have just UF that compute this, because that means you can just reverse all your gate inside your UF, then you will get the f of x and UF dagger equal to x. So yeah, so if you have this box for some one-way function, then you can just invert every gate inside inside your black box, and you can invert your one-way function very efficiently. And we kind of think that's not possible. Okay. Okay. So that's why we have this funny definition of quantum gate. So this is bait. Yeah. So we have this funny way to write quantum query that's reversible and actually don't let you invert one-way function. Is reversible for every f, and also don't let you invert one-way function, and that's this thing. So you keep your input x here, so you don't erase the information here, and output register, you can have arbitrary input quantum state, and you get this you get this XOR of your input with f of x here. Okay? And so make it reversible. And this allows you to do quantum superposition and everything that allowing this input state to be quantum, allows to phase feedback and interesting quantum thing. So you apply the UF as a quantum superposition. So by the quantum linearity, so we think about you have a superposition of different computational basis state. Then each one of them get apply UF accordingly. So x1, y1 plus x2, y2, then become x1, y1 plus f of x1, and x2, y2 all plus f of x2. Yeah, and so there's a difference between classical and the quantum query complexity, and actually there are also a lot of study in classical computer science that just study classical query complexity. So classical query complexity was different problem. A lot of them are also still unknown. Okay, and but back to the comparison between quantum query complexity and classical query complexity, it's very obvious that one quantum oracle is more powerful than is greater or equal to one classical oracle. So you can simulate one classical oracle with one quantum oracle, because you can just put 0 here, and then you have x, and go to f of x, and then you just don't use this x to do other things, then you can get your f of x to do whatever classical computation you want to do. Okay. And but then the study of quantum complexity theory, a big focus is thinking about what's the gap between quantum query complexity and the classical query complexity. So just what we see in the Deutch algorithm. So we think about different functions, so different quotient on this function f. So then we think about how big the gap can be. Is there a gap between classical query complexity and quantum query complexity, or maybe there is no gap? Okay. Yeah. And as we see in Deutch's algorithm, we have a very small separation here. So for this question of whether f of 1 equal to f of 0, we see that they require 2 classical query, but only 1 quantum query. And we'll keep seeing more quantum speed up, where there are bigger and bigger difference between quantum query complexity and the classical query complexity. Okay, we are exactly on time. So there's no question. Let's stop here, and we'll see the generalization of those algorithms on Thursday. and we will also probably see. Yeah, we'll probably also talk about midterm a bit on Thursday. Okay. Yeah. So see you on Thursday.